Okay. Good morning, ladies and gentlemen. Welcome in to ME3005 Lab. All right. I graded all the homework 6 that were turned in yesterday. So if you turn in a homework, your grade should be posted. Take a look at the solution. A lot of stuff with Hooke's law, stress and strain, kind of the foundational stuff of this class. So hopefully you kind of went through that homework and kind of understand. Definitely going to be a question on the next test about Hooke's law and 3D, stress and strain, etc. So make sure you got that. All right. I'm going to post homework 7 soon. I basically just put the finishing touches on it in like the last 2 minutes. So I'm going to post it right after the lab section today. That'll probably be due like next Friday. I'm going to give you a good amount of time on that. It'll be some non-circular torsion stuff and some pressure vessel stuff. So I'll give you a good amount of time to work through that. Okay. Today we're going to do the non-circular torsion lab, and that will be due 1 week from today. So last lab, I think kind of the calculations of this lab are more or less the easiest of all the labs. So you got that going for you, which is nice. So we're going to kind of go through the standard process today where we have a little bit of lecture material to talk about. And specifically, we're going to talk about some advanced strain gauge techniques. So I did post some lecture notes on Blackboard that talk about and show some of these advanced strain gauge techniques, and we're going to go through it here. But first, I do want to bring in the handout for the lab, which is also available on Blackboard. So let's bring that in here and we'll sort of talk our way through that first. All right. So this is available on Blackboard. This is our non-circular torsion lab. So today what we want to do is we want to calculate shear stresses from torsional loading at critical points of a non-circular member. So this kind of goes back to some of the lecture material that we've sort of been discussing so far with non-circular torsion. And so now we're just going to have a kind of a lecture or sort of a lab on it to sort of bring it home. Okay, so we're going to calculate theoretical shear stresses from torsional loading at critical points. And so the apparatus that we have is very similar to sort of the first lab that we did with circular torsion, what we called combined loading. Except now the cross section of this particular piece isn't circular like you had in the first lab, but it's rectangular. And so we're going to sort of do analysis on this guy. What happens when we actually put some torque onto this cross section? What are the shear stresses that develop, and how well does the theory predict what we actually measure in practice? Okay, so what we're going to do is put a series of strain gauges on here and wire them up in such a way that we only see effects of the torsion. Now, we know from some of the combined loading stuff that if we had an apparatus that looked like this, and we put a load kind of on this hook right here in sort of a downward fashion, you would induce in the cross section here not only a torque, but also a transverse shear. So if you're thinking about what's going on like at points B and points A on this cross section, you'd have some shear stress that would come from torsion, obviously, and you'd also have some shear stress that might come from transverse shear. But in this particular lab, we're going to do some tricky things with our strain gauges so that we can just measure only the effects of the torsion. And so we're going to talk about some advanced strain gauge techniques that we can do to just eliminate everything associated with transverse shear and only really look at the effects that are coming from the torsion on this piece. So that's going to be kind of the focus of the lecture today. The experiment itself is really quite straightforward. We're going to kind of take the apparatus like this, put one load on it, and then measure the strains from a variety of different strain gauges that are kind of on the cross section of the piece. You'll use those strain gauge values to calculate what the shear stress is at that particular location, and then compare that experimental value that you get from those strain gauges to values that you might predict from theory. All right, things that we talked about like in lecture and that you'll work on in this next homework. Okay, so that's the basic idea. The procedure here, the equipment here, this is pretty standard stuff for the handouts that we've had so far. So, we have a video for the experiment. I'd encourage you, after we go through the lecture material that we're going to do maybe over the next hour, after we do the lecture material, take a look at the handout in a little bit more detail, and then go ahead and watch the video. So a lot of things to consider and so on and so forth. So I encourage you to sort of look at that handout before you watch the video. Okay. Now, let's get into the actual lecture material itself. So we got to talk about some of these techniques that we're going to use with these strain gauges. We haven't really talked about before, because we're going to use strain gauges in a kind of a new way to isolate effects of just the shear stress that might come from torsion. So today we're going to talk about advanced strain gauge techniques, and specifically, we're going to talk about how to isolate effects of just torsion. So advanced strain gauge techniques. All right. So as I sort of mentioned, we've got this apparatus. It's got a rectangular cross-section. And what we want to do is we'd like the ability to wire strain gauges in a way that we only see effects of, let's say, torsion. So the question here is, can we wire gauges in a clever way, clever girl, to isolate effects of torsion? Okay, so what do I mean by that? Well, here's our apparatus again. It's this guy. Bam! You get lab apparatus twice. Okay. So what we're going to do is load this guy here with some load P, and I'm going to investigate kind of what's going on in this cross section here. Okay, so let's sort of like blow this cross section up. Okay, if you blew this cross section up and you looked at kind of like some of the points of interest that we care about in this particular lab, which are like sort of the middle of the long side of the bar and the middle of the short side of the bar, I know that if I were looking at kind of the combined loading on this particular guy, I would have a torque that would form, kind of torquing this cross section. And I would also have some load coming across this cross section, some transverse load, which I might call V. And so we know from our combined loading that, for instance, at this point over here, you'd have some shear that comes from the transverse shear, which is something like VQ on IT. And you'd also have some shear that comes from torque, which is sort of specific for a rectangular cross section, but it looks something like T divided by alpha A squared on B, where this is your side length A, and this is your side length B. Okay, so we have multiple effects happening, transverse shear and torque. My question then is there some way that we could wire strain gauges on our actual apparatus so that we only see effects of this guy here? If we could do that in an experimental way, then we could directly compare like our theoretical values, which we might measure as like that equation there, to what we're actually measuring from the experiment. So more or less getting rid of this noise here. So can we neglect this? And the answer is yes. And we're going to show you how to do that with appropriate wiring of strain gauges, but we have to go through a little bit of theory to get there. All right. So the answer is yes. You can eliminate transverse shear effects with a special type of wiring of gauges called a Wheatstone Bridge. So Wheatstone Bridge wiring scheme. Rawr! Exclamation mark. Wheatstone Bridge. All right. So the lecture over the next, 50 minutes or so is going to be how we get there. Okay, so let's break it down. And we're going to kind of start with sort of a simplistic case, and we'll build up our theory. All right, so let's first start by talking about two strain gauges arbitrarily in space. All right, so let's say we put two of our strain gauges just sort of arbitrarily in space, and we've got like an XY coordinate system here, and we're going to lay some strain gauges. Let's call it strain gauge 1 and strain gauge 2. All right, so maybe I've got one strain gauge over here that I call strain gauge number 1. And maybe I got one strain gauge over here arbitrarily in space that I call strain gauge number 2. Okay, so strain gauge number 1 is obviously going to measure epsilon 1. Strain gauge number 2, the output of that guy is going to be epsilon 2. We have this arbitrary XY coordinate system, and so we can sort of define an angle between where these gauges are and some axis of interest. Let's say the x-axis here. So maybe this angle here, let's call this theta 1. And maybe this angle here, let's call this theta 2. Okay. It's pretty similar to kind of like those arbitrary strain gauge equations that you've seen before in lecture. Okay. Now I want to know, let's say I want to know the shear strain at this point. All right. Can I do that with two gauges? Previously, we've required kind of a 45-degree rosette or 3 gauges at a point to fully define our shear strain gamma xy. But can we do it with 2 gauges? Well, kind of. So let's talk about this. We know from strain transformations the following to be true. If I want to write epsilon 1 in terms of this angle of theta, and maybe some things that I know about strain in x, strain in y, and the shear strain gamma xy, I could do that. So I know from strain transformations that like the strain in one direction, which I'm kind of measuring from this gauge, is this general equation here, which we learned in lecture. Okay. We can call this star because he's a star. All right. We have a similar idea that relates the strains in x and y and gamma xy to whatever we might measure in the 2 direction. So here this would be like epsilon x plus epsilon y on 2 plus epsilon x minus epsilon y on 2 times cosine. Oh, I missed my 2. This is 2 theta 1, and this is 2 theta 1. So this is cosine 2 theta 1 plus gamma xy on 2 sine 2 theta 1. Let's call this double star. Okay. I could solve these two simultaneously for this gamma xy term. If I'm interested in this particular term, I can solve these two equations simultaneously to sort of get that. So here, let's solve star and double star for this gamma xy. Do substitution, it's probably the easiest method here. And you would come up with something that looks like this. Here, this is 2 times the quantity epsilon 1 minus epsilon 2 minus the quantity epsilon x minus epsilon y times cosine 2 theta 1 minus cosine 2 theta 2, all divided by some other angular terms, which is sine 2 theta 1 minus sine 2 theta 2. Okay, this is just sort of rearranging star and double star together to sort of come up with this general expression. All right, well, in this expression, if I've got strain gauge 1 and strain gauge 2 on my piece that are sort of arbitrarily aligned in space, well, then I know the readings from those strain gauges. I know these angular measurements with respect to some xy coordinate system, but I don't necessarily know epsilon x and epsilon y, which is kind of a problem. And it's where we sort of get stuck if we're trying to solve for sort of the shear strain in this coordinate system is, well, how do I solve for this if I don't have the strain in x and the strain in y? And generally, you really can't solve for this shear strain xy if you don't have the axial strain in x and the axial strain in y, unless you could somehow eliminate this term entirely. So is there a way to sort of eliminate this term entirely? Then you would have everything that you know. So can we eliminate this? If we could get rid of that entire term, that would be nice. Then we would have everything that we need to calculate the shear strain here at gamma xy. Well, the answer is yes, we can eliminate that. And we can eliminate that if this particular term here or this particular term here is equal to 0. All right. Well, these things we aren't going to know, and we can't necessarily know. That sort of depends on the piece that we have. But we do have control over how we place the gauges on this piece. So where theta 1 and where theta 2 are, we can sort of control that. Where do I put my gauge on the piece here and the gauge on the piece here? These are things that we can control. So we could solve for gamma xy if this term cosine 2 theta 1 minus cosine 2 theta 2 were equal to 0. That would more or less get rid of this entire thing here, and we would have everything that we need to calculate that shear strain. Okay? So the question is, what conditions are this true? Well, there's kind of two answers to this. All right. And it happens, obviously, one case where it could happen is if theta 1 is equal to theta 2. So what does that look like? Well, that just looks like gauge number 1 and like gauge number 2 are like right on top of each other. Right? This is not a useful situation because what's going to end up happening is you're also going to cancel your denominator and you're going to have like a divide by 0 situation. So this is sort of a trivial case. Gamma xy will have a divide by 0. Which obviously we're not going to be able to solve for gamma xy when we have this divide by 0 condition. But there's one other situation where this particular expression can be true. And that's if we recognize that this cosine function is actually an odd function. So also happens if theta 1 is equal to negative theta 2. So that would look like the following. Okay. This is true because this cosine function is like symmetric about the x-axis. Okay, so here if this is theta 1, then here this is theta 2, which is negative theta 1. And this is like the non-trivial case. Okay, and this happens because, you know, cosine is like an odd function. All right, so then cosine 2 theta 1 is equal to cosine 2 theta 2, which is what we want, right? And that's because, you know, like if you resolved this guy to the x-axis, they would both sort of resolve to the same position. All right, that's the cosine function for you. All right. So let's look at this case a little bit more in depth, where this angle theta 2 is equal to negative theta 1. All right. So if this is the condition, we have the following. If we say theta 1 is equal to negative theta 2, and let's just call this the angle alpha. Let's just say this is some angle alpha. Then you end up with kind of the picture that I drew before. Then your shear stress equation becomes the following. Let's go back up and look at our equation. I'll give you a second to copy down before I move. So if this is true, then this term here will go to 0, and we'll just be left with sort of the other terms that are in that equation. So here this will just be 2 times epsilon 1 minus epsilon 2 divided by this other term sine 2 theta 1 minus sine 2 theta 2. Okay, so let's let theta 1 equals negative theta 2 equals alpha. And you'll have the following. Oh, sorry, 2 alpha. Sine 2 alpha minus sine negative 2 alpha. All right. Let's note here a following trig identity, that negative sine 2 alpha is equal to sine negative 2 alpha. And you'll have the following expression for the shear strain in this coordinate system given some equally angled distance between some axis that you know. Here the shear strain gamma xy is going to be 2 epsilon 1 minus epsilon 2 divided by sine 2 alpha plus sine 2 alpha since I'm sort of like eliminating this negative sign by trig identity. Or I can simplify this a little bit further and write that gamma xy, I can cancel a 2 here. So 2 is going to cancel. There's 2 terms in the denominator here. We can sort of see that. Very simply, epsilon 1 minus epsilon 2 over sine 2 alpha. Kind of slick. And the picture in your notes kind of does pretty well here. I'm going to pop that in. Bang. So that's what you kind of want to think about there. If you have 2 gauges that are equally distant from some x-axis with some angle of alpha, it's kind of like what I'm showing here. And the shear strain in this xy coordinate system is just given by this expression where you're assuming that you know the strain measurements from your gauges and coming off your epsilon 1, epsilon 2. Pretty cool if you ask me. All right, pretty cool. All right, we can go farther. Is it farther or further? I think it's further. We can go further because far relates to distance. We're not actually traveling any distance here. We're going metaphorically further. Okay, so let's go further. Can we simplify further? All right. How can we simplify further? Well, would be nice if this guy here were equal to 1. That would be nice, wouldn't it? Yeah, I think so. The sine 2 alpha term were equal to 1. That would kind of simplify the situation here, giving us a shear strain gamma xy that was just epsilon 1 minus epsilon 2, just the difference between the 2 gauges. That would be awfully convenient. So what values of alpha make this true? Okay. Well, when is the sine of an angle equal to 1? Well, it's equal to 1 if 2 alpha is equal to 90 degrees. So it's true if alpha is equal to 45 degrees. Okay. So in this special condition, where you have 2 gauges that are aligned at plus and minus 45 degrees with some axis of interest, then the shear strain at that particular point is just equal to the measurement of gauge number 1 minus the measurement of gauge number 2. That's pretty awesome. And that's what I mean by sort of leveraging some tricky techniques of multiple gauges. So there you go. And kind of the picture you should have in your head might be something that looks like this. Right. So I want to know the shear strain in like this X, Y coordinate system. These guys are at plus minus 45 degrees relative to that. So in this particular situation, the shear strain in this XY coordinate system is just the reading of gauge number 1 minus the reading of gauge number 2. Pretty freaking awesome. All right. This special arrangement of singular gauges has a specific name. And this arrangement of gauges is called a Shear Tea Rosette. Okay. And in this lab, we're going to use a Shear Tea Rosette. So we'll use this in our lab. All right, so I'll give you a second with the notes, and then I'm actually I have the apparatus here with me. I'll show you the shear tea that we have on this guy. Your notes actually have a couple of cool pictures of this. You know, you can buy these types of gauges like directly from the manufacturer. And so here are some examples of shear tea rosettes. Okay. So you can purchase gauges that look like this, okay? And so here's an example of one. This is an example of a shear tea rosette. It's Vichy 062 TV, my favorite type of shear gauge. Okay. So if we think about this as like, here's axis number 1, here's axis number 2, and we call this like X, Y. Or maybe it's easier to go the other way. Call this like X, Y. Right. Then we see that this particular gauge here has all these resistors that are kind of moving in this pattern, which is kind of like a 45 degrees with the x-axis. All right. The other gauge here, this one, which is like gauge number 2, has its resistor kind of moving in this way. So we see here that both of these gauges have like this plus minus 45 degree resistance orientation with respect to the X and Y directions. So this would give you your like plus minus 45 degree. So if you had like this was epsilon 1 and this was epsilon 2, then simply the shear strain gamma XY is epsilon 1 minus epsilon 2, right? Pretty easy to sort of understand that. Similar thing with like this next gauge, but this one's a little bit more complicated because it's sharing a lead between two gauges. So, okay, here's maybe your axis of interest. You see this resistor kind of at this plus 45 degree, this resistor sort of here at this minus 45 degree angle. And in this particular situation, the two gauges are actually sharing a lead, right? So this gauge here would be like epsilon 1. It has this lead and this lead. So you'd wire by sort of like soldering your two electrical connections to those points. And this particular gauge has a lead here and a lead here. So this would measure for you epsilon 2. So if you want the resistance of that particular gauge, you're soldering here and here. Okay, so we see that there's kind of a shared wire between the two. Kind of an interesting thing. As to the gauge that we're actually using in our lab, which is here. Again, it's got like this plus minus 45 orientation, and it's got a shared central lead between the two gauges. So here's the general idea. All right. So enough talky talk. Let's actually show this off. All right. Enough talky talky. Too much talky talky. All right. So let's actually show this off. All right. Here I've got the apparatus for our gauge. Thank you for spotlighting me, whoever's doing that. That's very nice. here I've got the apparatus. I don't have the steel through rod in. You know, the steel through rod would normally go through like the hole that's right here, and sort of kind of come out this way, and then we apply our torque. So I don't have it here, but you sort of see the apparatus has the same general idea. It's got this rectangular cross section. It's got a socket head cap screw in it right now, but the cross section here is about 1/2 inch by 1.5 inch, so an aspect ratio of about 3. Okay, so there you go. There's gauges in a couple of kind of key places on this guy. Obviously, you see the one that's kind of on the long side of the bar here. And then there are also gauges sort of on the top and bottom sides of this apparatus as well. And on the top and the bottom of this apparatus is where we actually have our Shear Tea Rosette. So this is kind of the top face. I'm going to do my best to kind of bring this in here and show this off. So here's the Shear Tea Rosette sort of on the top surface. Hopefully we can kind of see that. It's got one gauge at a plus 45, one gauge at a minus 45, and it's sharing a lead kind of in the middle there. So you see we have a black wire, a white wire, and a red wire. So if I wanted to measure like the resistance on the gauge on one of the sides, it would be like wiring the red and the white leads. And if I wanted the resistance of the other gauge, it'd be like measuring across the black and the white leads. So that's the general idea there. Okay, so there's your Shear Tea Rosette on the top surface. If I took the strain readings of those two gauges, the one on the left and the one on the right, and I just subtracted the two values that I got from that, it would tell me what the shear strain is on that particular point. Pretty slick, all right? So there you go. Shear Tea Rosettes and the theory behind. Back to the pad. Okay, that's a Shear Tea Rosette. Now, that rosette is useful in measuring the shear strain at the point on that apparatus. However, I have not talked at all yet about how we eliminate effects that might come from transverse shear or from torsion to only look at shear strains which might happen from torsion, or only look at shear strains which might happen from transverse shear. So yeah, it's nice that we got this gauge on there that can give us the shear strain, but the shear strain at that point that I would measure with that one particular gauge is not limited to just that of torsion or that of transverse shear. I still need to do something else to eliminate the transverse shear effects in my reading of that particular gauge. So how can we do that? That's the next step of the lecture, in eliminating some of these transverse shear components. So let's move on with that and sort of talk about this schematically. All right. So here we are. Let's talk about isolating torsion effects. Okay. I'm going to sort of proceed moving forward with like a circular cross section as a baseline, but the same theory that I'm talking about over the next, 15 minutes would apply whether the cross section is rectangular or circular or whatever. Okay, so let's consider a circular cross section. With torsion and transverse shear. All right, so a picture you might want to have in your head is some cross section that looks like this, and I'm going to apply a torque to it. So here, let's say double arrow. I've got some torque that's applied. This is like into the page. And then I also might have some transverse shear coming across the face, which I'll label with V. And maybe we put a coordinate system on here that's kind of a common coordinate system for us. It's like X, Y, Z. Or I think in the lab handout I use a little bit different coordinate system. So maybe we'll do X, Y, Z. I think this is a little bit better. So be consistent with the notes. Okay. Now I know if I have points that are sort of in the middle of the cross section on opposite sides here, let's call these points A and B. Here's A, and here's B. I know kind of from my combined loading history in this class that if I have a torque and I have a sort of a transverse load that are coming across, then I have shear stress contributions on either side of the bar that are going to occur both from the torque and from the transverse shear. So if I think about what's coming from this torsion, I'm going to have some component of transverse shear here at point B on the X face in the Z direction from torsion at point B. So I'm going to label it that way. And it's going to be pointing downwards because I think about like this torque giving me a clockwise rotation. It's going to be pointing downwards at point B. On the other side, I'm going to have the same magnitude of the contribution, but it's going to be in the other direction. So here, this is some shear stress on the, oh man, I don't like this coordinate. I'm sorry about the coordinate system here. I keep messing this up. I want to make sure I have the right coordinate system consistent with, there. Now we're good. All right. On the X face in the Z direction coming from torsion at point A. All right, so those are the shear stresses that I get from the torsion, sort of on opposite sides of the bar. And you kind of remember this going on in the combined loading lab that we originally had. Now, this transverse load here is going to give me shear stress as well, but it's going to be the same direction on both sides of the bar. So at point A, we have this shear stress on the X face in the Z direction from transverse shear at point A, which is sort of acting downwards. And it also acts downwards at point B from transverse shear. Okay. So we just kind of like know this to be true from our combined loading background. All right. If this is the case, let's talk about the shear stresses at each point. So at points B and C, sorry, A and B. Are going to be the following. Shear stress on the X face in the Z direction at A is going to be the combination of the contribution from torsion and the contribution from transverse shear. So that's going to be something like, I'll kind of have the directionality associated here. Since we're on the X face in the negative Z direction for transverse shear, I'll say this is the negative shear stress on the X face in the Z direction from transverse shear at A. Now I'm going to add to that the contribution of the torsion, since it's in the positive direction, here. Similar looking equation for the shear stress at point B. I'll have a negative contribution on the X face in the Z direction from transverse shear at B. Here, minus the contribution from the torsion at B. Okay. So this difference in the direction of the torsion is something that we're going to leverage on opposite sides of the bar. Okay, we'll make a note here that the magnitudes of these things are the same. That the magnitude of the shear stress on the X face in the Z direction from torsion at A is equal to the magnitude from torsion at B. Same thing for transverse shear. Okay, and that's because they're kind of like equally distant from the center, and the transverse shear is acting equally on both sides. Hopefully we sort of understand that. Okay. Since we sort of talked about shear strain up to this point, we want to maybe convert these stresses into strains. So let's talk in terms of shear strain. So we can divide all by the shear modulus G to get strains. All right, this just comes from like Hooke's law. So we're just going to rewrite these sort of in terms of the strains instead of the stresses. So here we have the shear strain at A is I just drew it as stress. Same thing at point B. Okay, so there we are. It's just dividing through by the shear modulus to give us everything in terms of strain. Okay, so we know these equations to be true just from kind of the theory of combined loading. Now, if I want to measure what is the shear strain at point A, what is the shear strain at point B, I could measure these using a Shear Tea Rosette. On sort of opposite sides of the bar. Okay, and so if I wanted to actually measure those values on opposite sides of the bar, I could do that with sort of like the following arrangement. So pictorially, this looks something like the following. We have this bar here. Okay, and maybe I'm looking at kind of like one side of this bar that, I don't know, let's say I'm looking at point B. But I know generally that if I'm looking at sort of the side of this, here's B, here's A. If I want to measure what is the shear strain at point B, I could do that with two gauges that are plus minus 45 degrees with my axis of interest. And let's say that my axes of interest are kind of like this coordinate system here that's like X, Z. Right? And I could label these particular gauges as like gauge number 1 and here gauge number 2. So if I wanted to sort of draw that on this picture at right, that would be maybe like this gauge up here, this gauge down here. We call this gauge number 1 and gauge number 2. These two things would give me the shear strain at point B. Let's say either way is fine. Kind of getting a magnitude of this guy. All right, similar idea. You could do this at point A by putting two more gauges. Let's call this gauge number 3, and we'll call this gauge number 4. Then the shear strain at A is 4 minus 3. So I can measure this. I can measure this by putting a shear T on opposite sides of the bar. So I have the following. It's this epsilon 4 minus epsilon 3. But I know this to be a combination of both the shear strain that comes from torsion and the shear strain that comes from transverse shear. So I know this to be like sorry. Plus what's coming from torsion. This is going to be strain 2 minus strain 1. And this is the negative minus that coming from point B. Okay. Here comes the magic. If I'm interested in only the magnitude of the torsion or the magnitude of the transverse shear, then I can strategically add or subtract these two equations here. What do I mean by that? Okay, if I add these two equations together, if you add these two equations together, this will cancel with this because they're the same magnitude. If you subtract these two equations, you can cancel the transverse shear components. And that's what we want to do. So let's subtract these two. Okay, so let's do that. The shear stress at A minus the total shear stress at B is going to be equal to the measurements that we get from those gauges but because we're subtracting them, I'm subtracting like this term from this term. And since they're the same magnitude, they'll just cancel out. So what you're going to end up with is this term minus the negative of this term. So you'll just get two of those torsional terms that rear their heads. So this is just going to be equal to 2 times the torsional shear strain. And since they're the same magnitude, you could say that it's whatever the shear strain is at A or the shear strain is at B. I'm more or less going to just drop these superscripts because we know that the shear strain from torsion at those points is equivalent. They have the same magnitude. Pretty nifty. So what does this mean? Okay. So then, if I'm only interested in what is the shear strain strictly coming from torsion, that is going to be the following here. I'll rearrange this slightly. This expression. To me, this is magical. Okay. You put some shear T rosettes on opposite sides of a bar. You measure the shear strains that are coming off of those particular gauges, and you calculate some equation here based on math, and you'll end up with just the shear strain from the torsional effects. That is awesome. Okay. To me, like the theory behind this and actually executing it in practice experimentally, it's what makes you a powerful engineer, understanding the theory and how we can apply the theory to actually making our lives really easy in the field experimentally. This is what they pay you the big bucks for. Okay. Any average Joe can slap a bunch of strain gauges on something and get a bunch of axial readings. Fine. Okay. Anyone that knows how to wire up a strain gauge can put 50,000 strain gauges on some apparatus and get you a bunch of axial strains. Fine. Not everyone can wire them up in a specific strategic way to just give you how much torsional strain am I getting at this point. That takes some freaking theory, and that takes some information and knowledge, which you're getting right here. That's what makes you powerful. Okay. All right. So the shear strain that's coming from torsion requires two of these shear tees on opposite sides of the bar. So I'll kind of show off the apparatus again. And remember on this apparatus that we have like a shear tee on the top side of the bar. So here's the shear tee on the top side of your bar. But to quiet effects of torsion, we need a shear tee on the opposite side to execute the math that I just talked about. So if I sort of flip this around as best I can, I got all these wires hanging out, and I show you the bottom side of the bar, you see that the bottom side of the bar also has this Shear Tea Rosette, which is kind of mirrored about this cross section from the top part, which I just showed off before is here. Okay, so you're going to leverage the Shear Tea Rosette on both the top and the bottom of the apparatus. You're going to get 4 readings, 2 from the top, 2 from the bottom. Those 4 readings are like epsilon 1, epsilon 2, epsilon 3, and epsilon 4 in this equation that I just wrote down. That will give you the shear strain that comes strictly from torsion. Pretty cool. We're not done. Buckle up. We haven't quite leveraged all the tools available to us yet. Last thing we want to talk about. Remember how we define or how we calculate strain from a singular gauge. Okay, this comes back to lecture number 1 when we actually talked about how to get strain readings from changes in resistance of a single strain gauge. So remember that the strain that we get from one particular gauge is the change in resistance divided by the original resistance divided by the gauge factor. And then GF is gluten-free. No, gauge factor. Okay, so these are your strain readings from a singular gauge. If we have strain gauges on our piece that all have the same initial resistance and all have the same gauge factor, we can do some simplifications. They have the same gauge factor and initial resistance. Then this shear strain that comes from torsion is going to be 1/2 times the strain gauge number 1. This is going to be like delta R on R1 divided by GF1 minus delta R on R2 divided by GF2 minus delta R on R3 GF3 plus delta R on R4 on GF4. If all of these initial resistances and all of these gauge factors are the same, we can just sort of pull them out and let them equal R and GF respectively. And you're left with this following equation. 2GF times your resistance, initial resistance of your gauge, multiplied by these changes in resistance of each one of the gauges. Okay. This here is just constant value. The gauge factor is a number, and the initial resistance of the gauge is some number. And we typically give this here called the variable phi. Right? So then phi times gamma x z torsion is equal to this change in resistance reading that you're going to measure from your gauges. Again, pretty cool. All right, constant value here multiplied by the torsional reading that you desire is going to be equal to these changes in resistance of each of the gauges. Now I want you to think back to your circuits class and think back to equivalent resistances for circuits. So this here is like a series of resistances of some circuit. Hopefully you talked about like parallel circuits, series circuits, how they sort of add together or subtract, etc. So the question then is, can we wire up our gauges in a certain way so that we read one change in resistance which has an effective resistance that's equal to this? So the question then is, can I build a circuit which has an effective resistance of R1 minus R2 minus R3 plus R4. So thinking back to your circuits class, you have some voltage here. You have some equivalent resistance. If I could make an effective resistance that went like that, then all I'd have to do is just measure the resistance of that particular built circuit, and that would be the shear strain from torsion multiplied by this constant value, which is just the resistance of the gauges multiplied by the gauge factor times 2. Okay, so can I build the circuit? And obviously the answer is yes. Otherwise, I wouldn't be talking about this. The answer is yes. And that circuit that you're going to build is called a Wheatstone Bridge. Okay. And the Wheatstone Bridge looks like this. This is your full sort of wiring schematic. Okay, here is your Wheatstone Bridge. Here. This is a circuit that would have an effective resistance that's like R1 minus R2 minus R3 plus R4. It's specifically designed in that particular way. Okay. So the idea here is that if I have some measurement lead here and I have some measurement lead here, the effective resistance across the circuit is R1 minus R2 minus R3 plus R4, which we know is simply just equal to whatever this torsional shear strain is multiplied by this phi constant, which is 2 times the gauge factor times the initial resistances of the gauges. That is just freaking cool. I mean, there's no other way to say it. You've got really deep theory here for strains, strain gauges, strain transformations. You've got really deep theory here for electrical circuits that are all coming together to give you one measurement that would give you the direct measurement of only shear strain that's coming from torsion. That is just cool. All right, there's just nothing else to say about that. All right. So in the lab, we wire Wheatstone Bridge configuration. And input the gauge factor and the initial resistance of gauges into strain boxes. So the readings from the boxes are the torsional values directly. There you go. So you'll see this in the video. You'll see me wire up all those gauges. Well, I actually won't do it. I cut away and then wire it. But I will wire up all of those gauges into that blue, strain reading box that we kind of saw in lab number 1. And I'm wiring it in this Wheatstone Bridge configuration. All right. And so when I wire it all up and you go to the strain box and you actually look at the values that are coming off of the strain box, those values are the shear strains that are only from torsion. Pretty cool. So that's it for the lecture material. The remaining notes that are there are just a little bit more detail on how the bridges are actually wired up. It's not really important for you guys because you're not actually doing the wiring. I actually did that for you. So I'll encourage you now to make sure you look at the handout, and then after you've sort of taken a look at the handout and digested it, go ahead and watch the video, which is the lab video here. It's maybe about 8 minutes long, so rather short. And that's going to be it for me. So go ahead and take time and do that now. I'll hang out here sort of in the chat if you have questions. Otherwise, your lab report due 1 week from today, and I'll see you guys tomorrow.